Hello, today we will be talking to you about the applications of electrochemistry and engineering relevant to energy transfers. Now, this all started out with Ben Franklin's shocking discovery of the electrostatic forces that are connected to lightning. Now, this basically allowed us to understand two materials, conductors and insulators. Conductors, which allows the free flow of electrons, and insulators, which prevented this flow.
Alright, so the first basic type of battery is a galvanic cell. Basically, it has two electrodes, a cathode, which loses an electron, and an anode, which gains an electron. And it has an electrolyte solution, which contains the ions, and the salt bridge enables the charge to not build up. If you make this reaction, it also has a wire connecting the cathode and the anode, allowing for electrons to travel from the anode to the cathode, propagating a charge which creates energy. And so if you allow this reaction to happen in the opposite direction, you can recharge the battery. So that is handy. It's called an electrolytic cell. Lead acid batteries were built off of the same principle with a lead oxide and lead as a cathode and anode and a sulfuric acid solution for the electrolyte. Each one of these systems produces 2 volts of energy, and if you put 6 of these together, it produces 12 volts of energy, which is enough to start a car. So these are widely used as car batteries, and they're the most common type of battery that is out there, most widely sold battery. That brings me to fuel cells. Cars are basically ran off of gasoline fuel, and they emit carbon dioxide, which is bad for the environment. Fuel cells rely on hydrogen and oxygen's attraction to each other to create an electron flow. So there's a catalyst, there's hydrogen and oxygen trapped into containers in a catalyst. The hydrogen goes through the catalyst, electrons split off of it. The electrons flow around a titanium membrane, which only lets positive hydrogen ions flow through. The hydrogen, electrons, and oxygens meet up, and so the electron going through creates the energy, and the output is water. So it's completely environmental friendly. The answer to the seemingly unending cycle of carbon dioxide dependence relies completely on renewable energy, the most vast source of which is provided by the sun. Solar energy can be captured by solar panels. These panels are filled with silicon, a semiconductor. Semiconductors have band gaps, however they are less than those of insulators. These materials can be made conductive by heating it or shining a light on it. In a solar cell, crystal and silicon is sandwiched between conductive layers. Solar panels utilize N-type silicon, which has extra electrons, and P-type silicons, which has extra places for these electrons to be stored. The p-n junction, or connection of these different layers, enables for one layer of silicon to have a positive charge, while the other has a negative charge. A photon can knock an electron loose, and this electron is drawn to the end of the N side, while the hole is drawn to the end of the P side. The mobile electrons are then collected by metal wires at the top of the cell. The electrons flow through in an external circuit, re-enter through the aluminum barrier on the opposite p-end, filling the hole. Each one of these panels produces about half a volt and utilize photons to knock off electrons, which promptly return to their initial position. This form of energy uses humans' greatest power source while eliminating carbon footprint.
Microbial fuel cells. Microbial fuel cells use organic materials to perform oxygen reduction reactions, which in turn creates energy that is stored in the cells. They work by harnessing the cellular respiration of bacteria between an anode and a cathode. When the bacteria oxidizes, the protons pass through a cation-specific membrane, which generates a current by the movement of electrons. Since microbial fuel cells rely on organic bacteria, the best place to set them up would be lakes with high populations of algae. The algae would continue to multiply, therefore allowing the expansion upon the system, as well as constant source of fuel for the cells. Another place often talked about is to set them up near wastewater treatment plants, which could take the waste from the plants and use it to cover fuel needs. MFCs can vary in size, so the applications are seemingly endless. However, as of now, they can only be used for low power operations until they are refined further.
Now I'm going to talk to you about the sodium and potassium gateways that exist in our bodies that allow for electrons to flow. Now, in our body, there exists an imbalance between the potassium and sodium ions. Now, in our cells, we have a cell membrane, and these membranes can open up to allow for the flow of electrons. Now, the positively charged ions that exist inside of the cells are potassium, but because of the anions, this now holds a negative charge. Now the sodium, which is also positively charged, exists outside of the cell. Now when the cell membrane opens up this gate, it basically allows for this potassium ions to flow outside of the cells, while the sodium, which are positively charged, are then attracted to the inside of the cell, which is negatively charged. And through this process, there is then a flow of electrons, which are these signals sent from our brain to our muscles that allows for movement. Now, this is basically relevant in engineering because in engineering, people are trying to build these electronic prosthetics that basically take these electrical signals and allow for these prosthetics to function. And so it is through this scientific phenomenon that if we understand it better, we would be able to build these prosthetics better.